Hello everyone, thanks for attending my talk. What I'm going to present in the next 45 minutes or so is my point of view from Microsoft Azure data of what's beyond the clouds. But let me get started. Let's start with what is Cloud 1.0. Cloud 1.0 was fundamentally a shift from on-prem scenarios to big, large shared data center infrastructure. Hardware visualization technology enabled this, and big business motions got a lot of the applications and services that were running on-prem to be moved into these multi-tenanted data centers where operations were automated and centralized and security was centralized. Now, why did people move in the cloud? Well, there's fundamentally because a lower and more progressive pay-per-use kind of cost infrastructure. The promise of this infinite scalability, you could simply rent more and more VM or less VM as your business requires, and simplified operations. What is typical though of Cloud 1.0 is fundamentally the fact the application didn't really change. If you had an application server talking with a database, well, now instead of having two servers on-prem, we have two VM in the cloud, but the structure of the application is fundamentally the same. So the question is, what is beyond the clouds? What above the clouds, right? So I'm going to describe this from the point of view of the Microsoft Data Platform, but I believe lots of the things I'm saying are also can be seen in other large cloud businesses. There are three main pillars that I'm going to touch upon in my presentation. The first one is cloud native engines. This is a very exciting time for database folks to be alive because while for a few decades, the structure, the architecture of our databases was fundamentally unchanged. We were just evolving the algorithms, evolving the features, but the big monolithic shape of a database was pretty much the same. By moving into the cloud, we found out that we can actually re-architect and redesign the engines to take advantage of the cloud in new and interesting ways. I'm going to touch briefly on this with a few examples. The second is an interesting motion towards unifying services. Instead of having a large scattered set of systems that you can wire together in your application, we're seeing more and more a motion towards bringing together multiple of these services and providing a more unified and simplified experience for the user. And the third one, which is what I'm going to spend most of the time in this presentation, is cloud tuning. It's an exciting new space where we can optimize the operations and the behavior of all of these systems because we can observe telemetry and dynamically tune the system, leveraging a lot of machine learning and data science ideas. Let me start with cloud native engines. As I was saying, this is a very exciting time to be alive. A very new, different engines. A lot of the cool research ideas are making it into now a big giant product. One interesting product in Microsoft is Azure Cosmos DB. This is a globally distributed, and I mean literally globally, like geo-distributed in all the regions around the globe, database system. It's interesting because it's massively scalable and it's multi-model. What I mean with this is that you can store the data and then query them as a key value store or as a document or a graphs or even SQL on top of the same underlying data. It leverages multiple consistency levels, which are very precisely defined. By allowing you to define your own resolution policies, you can get to 5 nines of availability while still meeting a 99th percentile latency of sub 10 millisecond across the globe. This is a new and exciting system. I link here a blog post that describes sort of some of the internal infrastructure. And as you can imagine, lots of research and lots of ideas went into this. Even all of the protocols have been proven with TLA plus kind of theorem proving mechanisms. Second one is one very close to my heart, is a new cloud native distributed SQL engine, right? So we took all of the experience, all of the learning from our big data internal infrastructure, and we fused them with SQL Server in a distributed fashion. So one of the key characteristics of this system is that if there are multiple in-flight queries, they all get merged in a single DAG, in a single graph of execution, and we can now automatically take advantage of some of the overlapping computation between different queries. It's also incredibly scalable and very high performance. The graph underneath is just one snippet from the paper, and it shows you that we've been running at 1 petabyte scale TPCH. I think this is the first time that has been done. And the results are actually quite good, about less than 100 minutes per query, even for the most expensive queries. And the team has been hard at work improving this, so I'm sure that by now the numbers are already better. And finally, I want to touch on another cloud native engine. This is also very exciting. This is SQL DB Hyperscale. This is, in a sense, a most prototypical way of getting cloud native, right? We took the classical way of doing OLTP databases, which is a single primary node with backup nodes for secondary reads, and we kind of exploded it, right? The computation remains the same, but the page servers that maintain sort of the buffer pool state have now been delegated to other servers that are connected with very high power interconnect, as well as the logging service infrastructure is also separate from the main machines, as well as the storage is pushed down to the Azure storage. So this is an explosion, right, that happened as a completely different architecture. And something like this could have not happened on an on-prem settings, because this is now a very complicated multi-service beast to deploy, right? And the very team that designed it and is operating at a very large scale at Microsoft has the ability, the cost, and the incentives to actually make it happen. While giving you something like this to deploy on-prem would be overkill and too complicated and too messy for even the most sophisticated users. So this is an example why moving to the cloud makes a lot of sense. And in summary, fundamentally here, we're taking the data and transactional state and we're sort of separating it from the computational pieces. This is the kind of motion you'll see in the cloud. Now, again, this is an exciting time for database researchers, right? Because these systems are real. These systems have been designed, invented, and put in production. So this kind of stuff can happen today. Next, let me touch on these unified services, right? And there are many examples, but I'm going to take the analytics example and kind of drive it a little bit through so you get a sense of that. So if you think about analytics, we're not in a world where you have a single all-up warehouse and that's all your analytics, right? The data variety is growing more and more, right? With the advent of machine learning and the ability to process multimedia data very effectively. Now, large amount of files or a big data lake full of videos or images is now an incredibly interesting source of data for analytics. Wiring into software as a service platform like Salesforce or SAP, it's also very interesting. Obviously, you're standard operational data, but you also have IoT devices that are now streaming in information about your business at a continuous pace. So the data variety is huge. And also the number of analytics operations you want to do on them is keep growing, right? We, again, used to have just a very simple all-up style reporting, and now we have sophisticated machine learning, big data style operation, business intelligence, and the classical kind of data warehousing. It's also becoming harder and harder. The governance and compliance aspects of data management are becoming more sort of demanding, right? So regulations like GDPR or the California CCPA are requiring very strict rules of how the data is maintained and stored and queried. Users have the ability to demand to be forgotten from the system, to their data to be deleted from the system. So in the past, all of this was solved by a collection of services, right? By a large series of services, each of which was very specialized. We had a streaming system, we have an all-up database, we have a Hadoop offering, we had like cognitive services that allow you to do sort of OCR or other sort of ML-based models on top of multimedia data. And you as a user had to fundamentally wiring all of these systems together. But now imagine to answer a GDPR style query where I tell you, well, now I'm Carlo, I want you to forget everything you know about me. Now you need to go across all of these systems and figure out how to chase my data around and delete them appropriately. Now the motion that we have done, the big push is towards unifying everything in a single analytic platform, right? So the various engines will still exist underneath, but now you have a single entry point with single billing, single security models on top of all of your data. Governance is integrated. Accessing data, moving data from one system to another is much simplified and much easier, right? You don't have to figure out how to export the data from here, write them in a file, read them from there, importing them. All of these things are becoming much easier, right? A single notebook experience on top of all of it. And this really allows you to cover the entire analytic continuum, going from your unmanaged data in the Lakehouse all the way to your transactional managed data in the warehouse, and anything in the middle like Delta Lake Iceberg style manage updatable files. And the kind of computation you can do are also very wide. You can go from machine learning to SQL to Spark to streaming, and there's no reason why you couldn't do SQL on top of your unmanaged files or machine learning on top of database tables. This is what we're empowering with these unified services. So far, the motion has been most an engineering motion, like bringing all the system together, wiring them all together. But I think there's a lot of interesting research that can come out here as well. Imagine a complex pipeline that starts with IoT devices, producing some data that is processed by a streaming engine, dump in a lake where through Spark you do some ETL and load them in a warehouse where you finally do reporting. Now we have an end-to-end system, and thanks to these unified services, we get to see all of them and we get to understand how things are wired together. So we can, for example, cross-optimize between engines. I can observe that your reporting is actually not using certain columns, it's filtering away certain columns. And then I can push this upstream to Spark and upstream to streaming services to optimize the entire flow of data top to bottom. This is the kind of stuff that we can do now. You can dream up in this space that was not possible before. In the rest of the talk, I'm going to tell you about cloud tuning. This is the some of the work we've been doing in my research group at GSL, as well in MSR, and I find it incredibly exciting in a new space, new era. So what's the problem with Cloud 1.0? Well, there was one only partially fulfilled promise, right, in Cloud 1.0. We told you, come to the cloud. You're not going to need a DBA in the cloud. That is kind of true, but not completely, right? So lots of the operations that DBA used to do, like setting up the backupping infrastructure for your database, guaranteeing high availability, upgrading the operating system, upgrading the security patches for your database. All of these things are pretty much done and automated in the cloud today. But there was still a lot that the DBA used to do. Like the DBA was able to see all of the queries of all the various users and define the right indexes, or prevent a certain expensive query to run on a OLTP workload, OLTP server, right? Not to kind of reduce the speed of certain transactions. So all of this workload management and tuning and optimization was part of the job of a DBA. And there's not really a completely automated replacement in the cloud. And in fact, by moving to the cloud, you even lose a little bit more control than you used to have on-prem. So that's a bit of a gap, a bit of a challenge. So what's above the cloud? How we go beyond this? Well, I think it's going to be a very sunny sky up there. And the way we're getting there is first by leveraging the telemetry that we have. For the first time ever, the people that are building the system, the building SQL Server, are also the people that operate it. So we can observe through telemetry what's happening in the system. Now, obviously, we respect your privacy. We don't get to see the queries or the data in clear form, but we get telemetry about, for example, which join operators are used most frequently. So we know to go and optimize those, or how to tune the amount of memory that is necessary to operate your system optimally. The second, there's been great advances in data science, right? We now can use off-the-shelf machine learning infrastructure that was not available just a decade ago. And obviously, we're going to throw a bunch of research, and with this, we're going to go above Cloud 1.0. But let me make this a little bit more concrete. Let's take one query, imagine a SQL query or a Spark query, and let's try to follow the journey and see all of the things we should be tuned all the way down to the physical hardware that are running in the data center. First of all, a typical question that we ask is, okay, tell us which VM type you want to run your query on and how many of them, like number of containers, for example. And this could be a static or dynamic decision. That itself is a very hard question, right? So we put this to the test a few years back. We made this very simplified scenario. We took 7 experts in big data. So these were either engineers with like 10, 15 years of experience in big data, or researchers that have been deep into the big data space. And we asked them, look at these two queries, query 1 and query 3 from the big bench workload, and these two cluster configuration in Azure. Same number of VM, 128 VMs each, and either D3 or D12 VM types, right? And to make things extra easy, we gave them the plan that Hive was going to execute the query with, and the cardinalities that traverse all of the stages of the plan, just to get a sense of how much data was flowing through. What was surprising is that all the users were quite off in their estimates, from over 5x overestimating the runtime of the queries to 20x underestimating the runtime of the queries, with the most expert engineers to be roughly in the right ballpark, but still even those were often off in terms of choosing which query would run better in which configuration. In fact, 6 out of 7 users were not picking the right order of which query was going to run better on which machine. And now imagine a standard user that runs an never seen before query on a much larger set of VM types, and potentially even controlling the number of VMs to run. Asking what is the right configuration is a very, very hard thing to do for the user, right? And only incredibly sophisticated user after lots of tries will be able to get it right. Another thing we have observed in our big data internal infrastructure is that for very important jobs, people are giving hints to the optimizer to make them run really well. And when I say very important jobs, I'm thinking about Bing monetization pipelines, right? So this is the money makers for Bing. Massive infrastructures, complicated pipelines, and these are very babysit by the engineers, and very competent engineers with a lot of time tune and tweak these jobs to their best. The kind of stuff they do, they provide hints to the optimizer of deep into the plan what is going to be the cardinality of a certain operator, right? After we traverse maybe several joins and several UDFs. This allows the optimizer to better tune the rest of the pipeline. Or things like hint about the skewness of the data, or tweak the cost models for certain operators, or even affect the search space of the optimizer itself. So these things are possible, are available, just incredibly sophisticated and difficult to do by yourself. Also, if you really care about performance, well, you should look at the physical data layout. You should choose the right format of data, the right partitioning, the right sort order, the right indexes built on top. And obviously, in the cloud, there's a lot of opportunity for caching, right? Your data starts from a remote store. We could cache the data there, but we could also cache them in your local SSDs, or in the main memory of the VM you're running on, or in the main memory of a nearby VM that is RDMA connected with high bandwidth to yours. And this is just where we can cache, but then what we can cache. Lots of possible strategies and mechanisms there. And again, all of this can be done, but it's quite sophisticated and quite complex for a user. And up to this point, I described mostly things that you can reach as a user. From here on, we start getting deeper and deeper into the system, right? We're moving to the right side towards the deep hardware side of things, where as a user in the cloud, you cannot even access this information. One that is a little bit on the edge is these ideas of scheduling or computational reuse, right? A DBA on-prem used to see all of the queries of all of the users and can define, for example, materialized views or indexes. We should automate this in the cloud, because if we promise that there's not going to be a need for a DBA, users don't get access to see each other's queries. So we as a system should be automating this step. Also, DBA used to schedule queries, right? Determine which priorities they have or what time they should be running. And this is stuff that, again, we could automate by looking at the provenance information or the dependencies between jobs when they run, and infer importance and deadlines. It turns out there's something we can do. Further down the stack, stuff start actually hitting the cluster, right? We start actually running on a physical cluster. So we need to determine things like, okay, how many tasks for every node that we have we should be running? Fewer tasks will run faster, but will have not as much throughput and will be more expensive, and more tasks will pack the hardware more densely, but they might running a little slower. What is best for the user? What is best for the operator? Let's try to optimize things. Similarly, we can decide to use harvest resources. If your tasks are reasonably short-lived, we could probably scavenge resources for a machine that is currently not fully utilized, right? Versus dedicating resources just for this computation. We also need to decide when to schedule management operations, right? We now decide when your backups are going to run. We don't want to run a backup in the middle of an important query, otherwise the query will run slow. So this is all just a few examples of what happened in the cluster tuning space. But we can push it even further. So let's really go to the extreme. We are the SQL Server team. We are operating SQL Server for you. In principle, we can go down deep into SQL Server, look at something like a spin lock wait time or memory allocator parameters, and tune those constants and recompile SQL Server just for your query, just for your database. So instance optimize the database for you. Now you can imagine that all of these things I'm describing were a sort of a big list of complicated things that need to be done in the cloud, sort of like an agenda for the future of research. And to some extent it is. But it's also a bit of a list of the things we have done. So this is a collection of recent paper in the last 2 or 3 years that come out from my group at GSL and from MSR on this sort of cloud tuning, instance optimize kind of work, right? And if you see, they're all across. Just I think 3 of them were just in the last SIGMOD we presented a few days ago. Even more exciting, this stuff is actually making into products. They're not just research ideas. They're research ideas that, and aspects of those are practical enough for us to deploy them and put them into the cloud, right? And put them into the services that you can actually use on Azure today. To give you a little bit more of a sense, I'm gonna pick the Cosmos internal infrastructure. This is like Microsoft Big Data infrastructure. It is where we usually start innovating just because it's internal. We have more visibility and more experience operating it, and more access to the users because they're internal Microsoft users. And I'm going to particularly focus on cost savings, right? So this is a very large infrastructure, so we want to save money, basically, reduce the cost of operating this infrastructure. And I'm going to give you a few examples just on that. And then we're going to dive deeper into how we've done some of these things. So this is a big numbers, right, to give you a sense of how practical this cloud tuning exercise is. So in this context, we have been using this telemetry plus data science plus research and sort of closing the loop to affect system. The first example is the $19 million for Yarn auto-tuning. Yarn is Microsoft scheduling infrastructure, so is an open source project. It's Apache Hadoop Yarn, and we use it for our Cosmos infrastructure. And by just tuning the parameters, things like how many containers do we run for every node, we were able to reduce the cost by packing the cluster a bit more densely by over $19 million. Notice that this parameter was a known important parameter that engineers have been manually tuned for like a decade. But still, through machine learning, through data science, we were able to tuning ever so slightly better and get these big wins. Another interesting project that relates to that is looking at how to reduce power consumption of our cluster. So we spec our cluster to run very hot because these are very, very busy clusters. But at the same time, we were able to see that if we actually underpower slightly, we reduce the power allocation for every rack. And then we use technology that will throttle CPUs if they were getting close to the power allocation. We can actually get a lot of power savings. And at the same time, by all of the telemetry we were able to observe that this did not affect the performance of our jobs significantly. So we were able to save about $30 million in power every year from our Cosmos infrastructure. And it turns out that since most of our data centers are power limited and not floor space limited, we were actually able to squeeze into the same data center more rows of machines and avoid building a separate data center. And so we save about $50 million in infrastructure as well, as a one-off. Also, we have been looking at the ability of harvesting cycles from the Azure infrastructure for some of our internal big data mechanics. And this is giving us a projected gains of about $70 million a year by just reusing unused resources from Azure. In more of the query optimizer camp, we look at the learning cardinalities, right? So this is the first, I think, production deployed learning cardinalities out there. And we're saving about 6% for applicable jobs. And in terms of computational reuse, this is a big one, right? In big data infrastructure, there's a lot of redundancy, a lot of replicated parts of plans for queries. And we have a mechanism, a system called Cloud Views that automatically look at all of the jobs running in Cosmos and find all of the overlaps and materialize all of the right views and reduce the cost for about $40 million a year. So as you can imagine, for each and every one of these data science in the loop, there's a lot of work that needs to be done, right? And if you look at the previous slides, right, where I was showing you the list of all of the publications, and imagine that for every one of those, we build this infrastructure and this data science loop, this would be incredibly costly. So it is vital for us to actually share a lot of the common tuning infrastructure, and then only change the algorithmic parts and the system integration parts, but reusing a lot of this infrastructure. So I'm going to briefly go over a pretty high-level view of this infrastructure. So I exploded now how the query gets to the database, right, with a simple query processing stack. So imagine optimizer, their schedulers, their runtime engines, and clusters. The most important first step here is collecting good telemetry, right? We want to instrument all of these components and extract as much information as possible in terms of which plans are being used by our queries, what does the scheduler choices are being made, the runtime, how much each task belonging to which plan is running on a machine, how busy was the machine. So all of the instrumentation and telemetry that we can. Now, as I'm going to show you later, this is a lot of data. It's in the petabytes, right? And so the representation of this data is incredibly important. As you can imagine, we can't just grab all of this data, dump it into a neural network, and hope for the best. Capturing, representing, doing the parsing, the normalization, imputing, cleaning of this data, it's incredibly important. So the same infrastructure can now feed the same sort of workload representation can now feed a large collection of different algorithms. So these are models, algorithms, and optimizations, each of which will target different part of the query stack, will focus on a portion of the data, and will try to predict, project, or optimize certain specific aspects of it. One of the things we learn is, rather than building single super large models that can predict the behavior of everything, we have been very successful in building sort of micro models. As an example, think about learning cardinalities. Instead of trying to build a cardinality learner for everything, we figured out that we could build specific models for the behavior of a join on top of these two tables, right? Subject to different filters. That could be one model. Another model could be another table, or an aggregate that behaves differently, or UDF that behaves different from the other. So the result is we have very localized, very specific models that are very, very effective, but we have many, many of them. So we have to build a serving infrastructure so that we can actually find the right models, serve the right models to the components that actually then use them, right? So this is the stats and insight service as this role of sort of collecting, gathering, and serving models. And finally, we want to close the loop, right, by feedback and actions, right? So we might have to modify the optimizer to be able to take into account these cardinality estimations that come from the model that are stored in the stats insight service, right? Or modify the behavior of a cluster or the runtime. Sometimes these are simple configuration changes, right? And I'm going to make an example of this, right? The infrastructure already has a configuration parameter, and we just simply set the configuration parameter thanks to this loop. Other times are very dynamic decisions that are being made by machine learning model integrated inside the system. So next, I'm going to take one specific example. I'm going to show you the Yarn auto-tuning project, and I'm going to show you sort of how this kind of loop looks like in practice for one specific project. So the project is called KIA, or Tuning an Exabyte Scale Data Infrastructure. This paper was presented just a few days ago at SIGMO 2021. And if you're curious about it, please go check out the original paper. So as a reminder, the Cosmos infrastructure is one of these like big data infrastructure, right? So we have a lot of job templates. Think about those as the recurrent job that runs every day. Each of those has multiple job instances, about 600,000 daily jobs. And those are comprised of multiple tasks, or sort of processes running on machines and running a specific computation, about 5 billion tasks. And they run across a large fleet of servers, about 300,000 servers. So the large cost of this infrastructure is our opportunity. And the size and complexity is our challenge. So there's over 10 petabytes of telemetries of logs that come out of this infrastructure every day. We need somehow to take all of those and use them in a data science loop so that we can reduce the infrastructure cost. The first phase is fact-finding and system conceptualization. In this space, a domain expert, for example, an engineer from either a research team or for a product side that is really, really familiar with the infrastructure, works with a data scientist. The goal here is to tease out characteristics of the system and simplifying the view of the system and extract a good problem definition. Very often, we're going to have the domain expert stating some facts that are believed to be true in the system, and the data scientist collecting data, measuring and validating these insights, and constructing a definition of what need to be optimized and what are the control parameters we have. The output of this is a problem definition. We fundamentally understand the configuration parameters, we understand what is the optimization we're trying to achieve, and we have some idea of what needs to be done in terms of modeling in the middle. The second phase is this modeling and optimization steps. We fundamentally take the controllable parameters, the configurations, and determine what are the performance metrics that are directly affected by the configurations. For example, if I control the maximum number of containers that can run on a machine, this will have an influence to the actual number of parameters of containers that runs on the machine. And then we use models to predict what is going to be the behavior on other metrics. For example, the CPU utilizations on the machines or the task runtime on the machines. And we can plug those into our optimization strategy. For example, we want the CPU utilization not to exceed, say, 95% of the resources, while trying to maximize the number of containers, so on and so forth, right? We want to get the best throughput, subject to certain latencies, etc. The result of this is what we believe to be an optimal configuration for our cluster, right? It's how the configuration parameters should be tuned to operate this workload optimally. Now this is not over. At this point, there's a long deployment phase, right? These are very massive cluster. They're mission critical in Microsoft. So we can't just take this configuration and just dump it into the cluster on 300,000 servers and see what happens. What we need to do here is what we call flighting and validation. So we fundamentally take a small portion of their cluster infrastructure, we deploy on it and test and verify. Just to be clear, at Microsoft, a small deployment is 5,000 nodes. And we can deploy on 5,000 nodes, see what happens there. If things go wrong, it's only 5,000 nodes. So we can recover from it pretty easily. But we get a sense of how things are operating there. If that works, we scale it out to more and more and more until we cover an entire cluster and we move it to other clusters. It's a long journey. Let me tell you a little bit more about this fact-finding and system conceptualization step, because I find it particularly interesting. So the game here is taming an intractably complex system. When we start, we have this big picture, right? And if you remember the number, we have hundreds of thousands of jobs running billions of tasks over hundreds of thousands of machines every day. And we need to look at maybe at least a month worth of data, right? So those numbers grow by 30 times. So how we do this? Well, the name of the game here is to try to find property of the system that allow us to simplify the modeling. We don't want to build a model for each and every one of the edges in this graph, right? That would be way too expensive, way too complicated. We will not have even enough data to train such a large model. So what we need to do is to try to find property of the system that we can validate that allow us to make some simplifying assumptions. One such example is that the job performance, which is ultimately what the users care about, is determined by tasks on the critical path. So far, so good. And the tasks on the critical path are very likely to land on machines that are either too busy or old and not as powerful. Well, we validated this statistically, right? Now, what I'm showing you here are always just intuitive graphs. There's a lot more sort of statsy heavy validation that happens behind the scene. But as you see here, for example, is we have Gen 1 machines, 1.1 and 1.2, and then Gen 2 and Gen 4 machines. What you need to know is that the lower number for the generations are usually older machines, and they're typically more utilized because we are very familiar with the hardware. We have been pushing it hard. So as you can see, the number of critical path vertices on those machines is disproportionately high with respect to all of the vertices running on the machines, right? Now, newer generation machines can run more containers, and we have more of those machines, but there are fewer critical path vertices. This is telling us that we don't have to focus on job level SLOs. We can go down at task level SLOs and just trying to get tasks to go fast. And in particular, we can just look at machines and try to get machines to behave better. Now, another thing that we need to validate though is that the same type of tasks are landing on the machines, right? I mean, a machine could be running slower just because it's running more expensive tasks. So another validation, another insight from the domain expert was our scheduler is pretty good at spreading the task uniformly across the machines. We validate this numerically with statistical validation. And here's just a graph to get you the insight of it, right? So here we're showing different racks on the left side and different generations of machine on the right side. And the color represent the different types of operators that are being running on the machine, right? And as you can see, they're very even across the different racks or the different generations of machines, right? So it's true. We showed that it's true that the tasks are mapped to machines very randomly in a pretty uniform way. So now we don't even have to look at tasks individually. We can look at the behavior of machines. So at the end of the day, we can just look at machine groups and create single models for machines groups. Right? We can model Gen 1.2, Gen 4.1, and so on, right? Different generations that we have in the graph. We don't have to build a model for every task on any machine and any job across the game. What do we do with these models? Now we have models at the machine level. What we can do, we can plug them in an optimization infrastructure that tries to tweak the number of containers running on the machines to produce an optimal configuration. In this case, the goal is to run as many containers as possible in the cluster. This will reduce costs and increase throughput, while maintaining the same level of performance. So we want to make sure that the users don't get any visible reduction of job performance, right? So we want the slow tasks, the one that are on a critical path, not to get slower. In fact, if possible, to get faster. But we basically bound the CDF of tasks so the tail doesn't get worse, And other than that, we just want to get more out of the cluster. And it turns out that this works, and it gets us about $90 million a year from our infrastructure. Interestingly, the very same infrastructure, the very same data, the very same model can also be used for sort of hypothetical tuning. In this case, what we want to do is predict the future and predict how this hardware would run if we were to build new machines that have different characteristics. The common problem in designing new machines is to pick the right set of resources, so CPU, RAM, and SSDs, so that we get the most out of the machine without leaving any of the resources stranded. So ideally, we want to get to all of the resources getting choked at the same time, and not running out of RAM before we run out of CPUs, or running out of SSDs before running out of RAM. So interestingly, what the team has done historically, it was also always considering CPU the most expensive resource, and so try to buy enough RAM and enough SSDs so that we could fully utilize the cores. Now, if you look at the cost trends, they're a bit shifted. The CPUs are not as expensive as they used to be with respect to RAM and SSDs costs. So what we found in this exercise was that actually the optimum point was not really high up in RAM and SSDs. It was actually quite conservative in terms of the amount of RAM to associate to a machine and SSDs. In fact, the optimal point was about 250 gigabyte of RAM for a 128 core machine. We used to buy like 700 or a terabyte of RAM for a similar configuration. And what you can see is that an interesting shape of the space where not enough resources SSDs and RAM are very expensive, because we will basically throttle CPUs and just waste cores that we bought. But also too much RAM or too much SSDs will become wasteful in other ways, right? And so the optimal is somewhere there in the middle. So with this, let me jump to another project before I conclude. This is the MLOS project. This is an open source project, and the idea is to go even deeper into the system, right? So here, if you remember in my slides with all of the different things we could do, I was telling you, hey, maybe we can go deep inside SQL Server and tune an internal parameter just for your database. The MLOS project is designed to do that and enable this kind of data science-driven performance engineering. And it's a toolbox, it's a developer toolbox for making this easier to access. I'm going to start with a motivation, right? So this is an actual line from the SQL Server commit log. I kind of simplified a little bit, but fundamentally, in this commit log, we are changing how a hash value is computed for a certain internal part of SQL Server. And you can see that the main changes were changing 50 that was multiplying a certain parameter to 53 and adding a 7 multiplying another parameter. Now this came from a customer complaining there was a performance bug. This led some spin lock being particularly costly, and it was due to the hash function not projecting sufficiently uniformly the data across different parts, right? So there was accumulation basically on one of the buckets. Unfortunately, what we found is that in the log, there was just a brief comment about this user had a performance issue. We're changing 50 to 53 because it's a prime number and should work better. And that's all we know. And this is very common of standard traditional software performance engineering. Developer gets a piece of code that is not running fast. It changed something in the code. It recompiles it, deploys, runs a benchmark. Doesn't work. Change something else in the code. Recompile, deploy, runs a benchmark. It works. And that's it. The only thing we remember is that now SQL Server has 53 in it. So what is the problem with this? One, the entire process is incredibly slow. Like this loop where I recompile SQL Server every time is quite daunting and slow. Two, it's poorly documented. We don't know why it's 53. Three is very brittle, right? This might be a fixed something for this user. We might have broke somebody else's performance behaviors, but we don't know, right? It's repeated, right? This needs to be done for every hardware generation, for every performance bug, and it's a pretty tedious process that we need to do by hand every time. And finally, it's exclusive. There's only a handful of people at Microsoft collaborating often with Intel engineers that really knows and understand how to do this work, right? And we want to make this, obviously faster, cheaper, better documented, less brittle, and automated as possible. So this is the goal of the MLOS project. I'm only going to give you the intuitions of the project. The insight here is to basically get away from hard coding constants to the system. we're just going to define parameters. We're going to register a parameter with the system. And through code generations, we're going to be able to make those observable from the outside of the engine. We can ask user to define performance unit test or all-up benchmark for the entire system. And in an external agent, we can now control policies and that define how those parameters should be set. And in particular, we're going to use a Bayesian optimizer that ships with MLOS to tune those parameters. So if you see what's happening here, the loop I was describing before now is done at development time, right? I can take this entire software performance engineering loop and fundamentally automating it. I'm going to expose some of the parameters. I'm going to hook up a Bayesian optimizer and I'm going to allow you to basically loop around it automatically. Now, one of the things we notice is once you do this and you find an optimal, very often engineers wonder, why was that the result? Like, what is the intuition behind it? So the entire experience is really wrapped in a trackable and interactive experimentation platform. Think about it as like a notebook and a data science experience that allows you to sort of see what's going on, understand what's happening. In particular, one thing that's very interesting is once you have performance unit test or all-up benchmark, we collect a large number of hardware and OS metrics, and we use those to try to explain why the model is making the choices it's making, right? So they're used not only to feed the model to make the right decisions, but also to explain why the model looks the way it looks. Anyway, MLOS is open source, so please check it out if you're interested in applying it to your services and systems. It's out there at Microsoft GitHub.io/MLOS. So you should definitely check it out. So what are the lessons learned we had over this entire journey? First of all, you lack telemetry. Doesn't matter what project you want to start, there's not enough telemetry. You need to go back into the system, change something to just correct more information. So when you build a new system, when you deploy a new service, collect as much telemetry as possible. Will make your life easier later. Second, it is all about the infrastructure. This data science loop is rarely about capturing the best model. Very simple models are often enough. It's all about building all these pipes and data transformation and guardrails around things. So invest in good infrastructure. Third, insights are typically more important and come earlier than automation, right? What we notice is that by setting up the right telemetry and having this automated infrastructure, we often provided insight to the engineering team that allow them to solve problems and make engineering decisions much before we were able to automate anything. Finally, you can't afford to redo this for every engines, for every applications. It is important, it's fundamental to share infrastructure pieces across, right? And lastly, you can have a DNN once you show me you can be trusted with a linear regression. This is obviously a joke, but it's just to give you the idea that simple models are often preferable in this scenario, right? They're more explainable, they're more clear, engineers will trust them when they need to be deployed in production, and we really only escalate to fancy models if it's strictly required. So in summary, get some good telemetry, build yourself some useful infrastructure. This will give you insights. The insights will allow you to get to the right automation, solve the right problems, and finally, having fancier and fancier model as you go ahead. And finally, we might even need some new machine learning to be invented for the problem you have, but that's pretty far away. So what's beyond the cloud? Well, we think is a sunny future where we have unified services that are made up of cloud-native engines, and we're going to tune all of this with this data science techniques that I described. This will conclude my presentation, and I'm available now for questions. Thank you.